Hello again. So after having familiarized ourselves with the physical modules of the InnoSpaceTool, we are ready to actually get into the interface and learn how to control them and how to measure what they do. So this is the interface I have in front of me. Once you have connected all three modules to your computer, this is what you will see. And you see three main tabs in the user interface. First one called transmitter, second one called free space, and one called receiver. And you can use these three tabs to manipulate different properties of each of these three segments of the communication system. So on each of them, on the top, you will see something called port, and this port tells you to which USB you are connected. So for example, the port of the transmitter, it could be COM3, it could be COM9, it depends on your computer, but it tells you which USB port is connected to the transmitter. Then again, you have port for the free space and port for the receiver. And essentially this tells you how each of these three segments communicate with your system, with your computer. So the second thing you see here is the baud rate. And this baud rate, it is not the rate of transmission between the system, the three segments of the system. It's the transmission between each of them and your computer. So this actually tells you how fast each of the three modules is communicating through USB to your personal computer. And you can change this, but we usually keep it fixed, this 111,000. And essentially these parameters are not really for you to switch. They are more or less fixed. Once you have set up which USB ports are used in the system, you don't have to manipulate them. Also, the address is something which you are not supposed to manipulate. So this is something which identifies each of these devices in your local system, and this is more or less fixed. So the first three fields of each of the three segments, the transmitter, the free space, and the receiver, are fixed. And the rest of them, however, you can manipulate and you can use to simulate any sort of communication in a variety of possibilities. So you see on top of the interface, of the whole interface, we have several buttons which are basically start transmission, stop the transmission, some settings, refreshing the COM ports, because if you have just connected the new USB port, you should refresh to find it. Also, we have some logs, which is a folder which records anytime you do transmission. It will record basically the properties of the transmission, how you are transmitting, with what rate, what frequency, and so on. And also you have three possible ranges of frequency, which are UHF, S-band, and X-band. So if you recall from the theory that we had, essentially UHF is around 430 to 450 megahertz. S-band is in the range of a few gigahertz, and X-band is even higher, up to 8 gigahertz. So these three bands, they are used in our module, and although the physical modules, so the physical RF components which we saw, which we connect and which act as real transmitter and receiver, they only use UHF, we are using essentially different parameters in them to simulate the other two. So we are simulating S-band and X-band transmission by feeding different parameters to the UHF transmitter, and essentially it acts as if we are on those higher frequencies. So you recall from our theory that the main segments of a communication system would be the transmitter, the receiver. Of course, we might have some amplification, which is the antenna. And in this case, we have all of these as well. And we can also manipulate the free space in between the transmitter and the receiver. So we can insert noises, losses, and so on. Now, the first thing which you can actually manipulate is the frequencies of the transmitter and receiver. So you see, for example, in my user interface right now, it's set to 437.5 megahertz, the frequency. I am on UHF, and you can change this. For example, if you go to S-band, you're going to start from 2000 megahertz, which is 2 gigahertz. If you go to X-band, you're going to start at 8000 megahertz by default, which is, again, it's 8 gigahertz. So you can change those frequencies, and although in reality, again, the modules themselves, they work on UHF, all of the losses, all of the mismatches, they're going to be calculated in such a way as to simulate what would happen on the other two bands. So apart from the frequency, the next, I'd say even most important thing to consider for the communication is the modulation scheme. So the modulation which our modules use and the modulation you're going to be playing with is called GFSK. So you remember FSK, the frequency shift keying, which in the theory we reviewed quite thoroughly. It was using essentially a small frequency deviation, which was giving you a slightly higher frequency or a slightly lower frequency, depending on the bit, is it 0 or 1. So GFSK is the same thing, but there's also a letter G, which stands for Gaussian. So it's an FSK modulation, which uses a Gaussian filter. And we also reviewed some Gaussian filter, and you remember that it cuts the harmonics. In this case, we are not cutting harmonics. We are essentially, in the time domain, we are smoothing out the transition between the two frequencies. And this smoothing out of the frequency transition, it results essentially in, again, in a type of a cutting of harmonics with a Gaussian profile. So you can see several options in this menu here. So you have, all of them are GFSK, so the same type of modulation, frequency shift keying, but they have different numbers. So the first number tells you the baud rate, so the symbol rate at which you're transmitting, and the second symbol tells you the frequency deviation. So this, for example, 2400, it means that you have 2.4 kilohertz of difference between this delta, which you add or remove from the carrier frequency. You can play around with this, and you can see that if you have a smaller frequency deviation, maybe this will be more resilient to the nearby transmissions because you're going to be in a more narrow range. On the other hand, it may be harder to detect by the receiver. So you can play around with this, and you can see that the same type of modulation, just changing the parameter, so this delta omega or delta F, depending on how you label it, just changing it can actually change the communication significantly. So the next menu you have here, the next drop-down menu, is the TX, so the power of the transmitter. Now you remember that we calculate power either in watts, or we convert it more conveniently to decibel watts. Here what we have as a measurement is decibel milliwatts. So in reality what we do is you put some value for the power of the transmitter, but there is a different value which is used in the communication module just for safety reasons. So you see here in brackets there is real. For example, in 20 dBm, there is real minus 10 dBm. So when you were when you're simulating 20 dBm power, in the physical device in which you are connecting to the computer, it's actually using minus 10 dBm. This is just to make sure that there is no too much radiative losses, and for safety reasons, the people around are not exposed to too much power. So you have several values you can use for the transmitter, and you can play around with them. And once again, you can see the good old formulas we've had, that the power of the transmitter, how it's related to the power of that is received in the end. And you can play around with these values. You can look at different noises and see that if you have higher power, maybe this doesn't help at all because the noise might also have high power. Now, the next parameter is something very crucial, which you should remember as being one of the most important values. So this is the antenna gain, and here we have a rather limited range depending on the band which we're using. So you can see that for S band we have higher possible antenna gain. For UHF we have lower possible highest, let's say, value of antenna gain. So depending on which band you're at X band you may have a much more directive antenna, but you remember that higher frequency will have more losses. So you can see all of these details here. And for example, in UHF right now, I am putting 2 decibels, and you remember that this decibel notation here, it's dBi, so decibel with respect to the isotropic antenna. And again, you can use this and change the value of your antenna gain just to see how this changes the final link budget. So we see one more loss parameter in the transmitter chain, and this is the feeder loss. Now, we were speaking in the theoretical part about ohmic losses, about the effective area, Now this feeder loss, it's essentially the losses you have in the region before you actually get to the antenna. So after the transmitter, but before getting to the antenna. So in some sense, these losses, depending on the convention, they may be included in the final effective area, but you have to take them into account. So these are additional type of losses which are due to the transmission from the transceiver, or this transmitter in this case, to the antenna. And we simulate again these losses. So they will be added to the final link budget, and they are something which in reality you have to take into account, the implementation of this feeder. The other three fields you see here, so the payload size, the packet count, and the delay, they are related to, let's say, a different type of communication which we're using here compared to what we were used to. So we have what is known as packet communication, and we were so far speaking about bits as basically as being our smallest unit of things being sent. Now packet communication, again, it's digital communication. It uses bits again, but our payload in this case are the separate packets which are, let's say, a combination of bits. So we assemble many bits together, and what we get is a packet. And this packet, it has preamble, it has the structure of having a preamble, of having some indicator or name or address of where it should be. And then it has, let's say, the payload of the bits, which is the structure, the main structure of this packet. So you see here several options for the packets. And the first thing is payload size. And this tells you how many bytes each packet has. So it's not the number of bits, it's number of bytes. And in the binary case, we have bits, and what we understand by a byte is usually 8 bits. So what we have when we put here 11 for payload size, it would mean 11 bytes on every packet. And on the next field, you actually have the packet count, so the number of packets, which in this case we're sending 1000. So each 11 bytes are paired together, and they're turned into one packet, and then we send those 1000 packets. So in a sense, it's a way of reassembling a long sequence of many bits into a smaller sequences of packets in such a way that each packet, it has a directory and it has some sort of address, and they're all added up in the end, but we are not sending them as one long sequence, but instead as shorter sequences, so that we can find out about each sequence where it should be in the whole thing. And it's, in a sense, it could be more secure that you know that each packet was received, and if you have a wrong packet, only you need to re-receive that one and not the whole sequence as a whole, because you know exactly where it is supposed to be. It has some sort of address. Now, the last field you can manipulate here, it's the delay in milliseconds, and it's rather self-explanatory. It's time delay in between packets. So if you have 100 milliseconds of delay, this means that once the first packet goes through, there is 100 milliseconds in which basically you have silence until the next packet starts, or you have some sort of a message which is characteristic for the transmitter, but not information, not payload, until the next packet is sent. And you can play around with this parameter, and you can see that this delay also, it governs the let's say the reliability of the communication, because if you have too small of a delay, essentially if you put the delay equal to 0, then all of these packets, they're sent as one big packet. There is no delay in between them, and this may worsen the communication. You can actually check how the total error rate, so the packet error rate, is changing depending on this value. And once again, you see in the receiver window down that we have switched from bit error rate to packet error rate. We have essentially the same things in the receiver chain. Of course, we cannot manipulate the payload size and the count, because the transmitter is deciding what it's sending, but you can see essentially the same parameters in terms of the frequency which the antenna is used, the receiver antenna. We have again the gain of the receiver, and we have the feeder loss. So the same 3 parameters which we have been considering also in the theoretical part.
Now, in addition to those, you see one more field which is called frequency compensation, and it's in kilohertz. Now, later when we look at how we can simulate Doppler effect in the device, you will see that this frequency compensation is actually the internal compensation that the receiver can do to compensate for the frequency deviation. So you can play around with this field later alongside with the frequency itself to see how, if you do not compensate, you have to manually receive at a different frequency, slightly different one, depending on your Doppler effect, which might reach up to a few kilohertz. Now, something additional you can see is that if you are transmitting at 450 megahertz and your receiver is at 449, for example, you will not be able to receive because this frequency deviation is too high, and simply you have a very small frequency deviation which cannot be captured by this difference of a whole megahertz, because in this configuration of the GFSK you have just 2.4 kilohertz of deviation. And you can see if you change this frequency of receiving, and also based on your Doppler effect with no compensation, you can see when you actually get to a real receiving.
In this case, we have on the order of a few kilohertz of frequency deviation. So if you go a whole megahertz away, you will no longer be able to detect these deviations. So you will lose the communication. And you can actually check out how you can manipulate and change and slightly offset the frequency of the receiver and transmitter, and see how the communication worsens in these cases. So we also have, of course, the modulation scheme. So again, only GFSK, but you can play around with the different types of GFSK. And of course, to receive properly, we need to have the same modulation scheme as the demodulation scheme. And of course, the antenna gain, which can be much larger on the ground. So we are actually simulating, let's say, communication with a satellite, which might be transmitting with a less directive antenna, or maybe even omnidirectional antenna. But the receiver might have a much better gain, and so you can see how, again, the play between transmitter and receiver gain is giving you a better communication. And again, do all of these mind experiments with maybe having a more expensive antenna on the ground, but having a lighter satellite, or vice versa. And again, the parameter of feeder loss, it is essentially the same as this parameter for the receiver chain. So this again gives you a sense of efficiency between the receiver and its antenna. So in a sense, the antenna will receive some RF power, it will convert it essentially to an electrical signal, and the signal, until it actually reaches the receiver, there may be some losses due to the feeder, and this is taken into account here.